Power of the z-test for proportion, section 8.1. Consider again the following hypothesis test. For a sample of n equal 100 patients, the proportion cured by new drug p hat 60 over 100 is 0.6. We tested H naught, p equal 0.51. New drug has the same cure rate as the old versus HA, p greater than 0.51. New drug has a better cure rate, and concluded with 90% confidence that the new drug was better than the old. The Greek letter alpha represents our desired maximum probability of a type 1 error, which is the probability of rejecting H naught if H naught is true. It is also useful to consider the probability of a type 2 error, which is the probability of failing to reject H naught if HA is true. So usually in practice it's rare to compute the probability of a type 2 error because we don't have a specific value for p under the alternative hypothesis. In order to compute it, we need to put in a particular number for p. We could pick any number bigger than 0.51 for p and get a different probability of a type 2 error. But sometimes it's useful to just say play what if and say, well, what if p was really 0.7, what it would be the probability of a type 2 error. So that's what we're going to do here. We're going to say, well, what if p was the actual population proportion is 0.7? What is the probability of a type 2 error? So beta, the probability of type 2 error, is the probability of failing to reject H naught if HA is true. And that would happen if p hat minus p0 times square root of n over p0 times 1 minus p0 is less than z 0.5 minus alpha if p is actually equal to 0.7. And if we plug in the numbers, we don't want to put in a number for p hat because p hat varies from one sample to another, and we're going to treat p hat here as a variable. So p hat minus p0 would be 0.51 times square root of n is 100. Square root of p0 times 1 minus p0, that's square root of 0.51 times 0.49. And the number from the z table would be 0.40. Okay, so then we look up the number in the z table. It's 1.282. It's actually our table doesn't carry to the thousandth position. It's actually between 1.28 and 1.29, but I was guesstimating 1.282. But you probably 1.28 would be good enough. Okay, so and if we multiply, I computed square root of 100 divided by square root of 0.51 times 0.49 is 20 point something, and divide both sides by that, and we get p hat minus 0.51 is less than 0.06 something, and add 0.51 to both sides, we get probability of p hat less than 0.57, and that's if p, we want to compute this probability if p is actually equal to 0.7. So now we can plug in the 0.7 here, and compute another z-score again, and it's 0.57 something minus 0.7 times square root of n, which is 100, over square root of 0.7 times 1 minus 0.7. And that comes out to be negative 2.75, because our table doesn't have the negative z-scores in it. We'll write this as 0.5 minus the probability that z is between 0 and positive 2.75, and 0.5 minus 0.497 is 0.0030. So the probability of type 2 error is pretty low. It's even lower than our desired chance of a type 1 error, which is reassuring. However, this calculation is based on a guess that the cure rate of the new drug in the long run is 0.7. So the actual probability of a type 2 error could be either higher or lower, depending on what the actual cure rate of the new drug is. And then the power of the test, part B, it's 1 minus beta, or 1 minus the probability of a type 2 error. So it's going to be 1 minus 0.003 or 0.997. So the power of the test is even greater than our desired confidence level, which is reassuring. But again, this calculation is based on a guess that the cure rate of the new drug in the long run is 0.7. The actual power could be either higher or lower. And a reminder again that type 2 errors and powers are rarely computed because we don't usually know the actual population parameter, and therefore our calculations are hypothetical. In this example, we can only say that if the proportion cured in the long run and the entire patient population is 0.7, then the probability of a type 2 error is 0.003 and the power is 0.9970. And that concludes this presentation.